Hello and welcome everybody to this webinar from the ESA CCI program. Thanks for joining us. This is actually the first in a new series of webinars under the CCI Knowledge Exchange activity that we're calling Monitoring Climate Change from Space. And it'll be a monthly webinar series that will cover a wide range of topics across the climate change initiative. So I'm Ravi Kapoor. I am the Managing Director of Imperative Space. We have a role in the ESA CCI activities, principally supporting knowledge exchange with a particular focus on training. We've been conducting a range of seminars and training events and interactive opportunities for learning about climate data using Jupyter notebooks and similar tools. And now we have this webinar series that we hope will bring the possibilities of what the data can support to a wider audience and in new ways. And today we're going to be focusing on greenhouse gases. For those of you that don't know, the Climate Change Initiative is a long-running, ongoing activity that systematically looks at each of the so-called essential climate variables in incredible detail, with teams of scientists looking at the data, reanalyzing it, and exploring the trends that it reveals. And presenting today on greenhouse gases, I'm delighted to welcome Dr. Michael Buchwitz. Michael has, since 1993, been pioneering satellite retrievals of greenhouse gas data at the University of Bremen. He is the science lead for the greenhouse gases essential climate variable project within the CCI program. And he's going to talk us through today some of the fundamentals of how the analysis and the process of working with greenhouse gas data works, and also give us a sense of what the signal in the data is indicating at this time. So without further ado on any of that, we'll just pass over to Michael. But I have just remembered there's one more thing I do need to tell you all, which of course we do have the opportunity for you to ask some questions as well. So please do enter any questions you may have for Michael at the end of his presentation into the Q&A box that's available to you, and also into the chat. Both mechanisms will reach us. And I think on your screens shortly there will be a poll for you to answer a couple of questions about your prior knowledge of the CCI program and indeed climate change and the data more generally. Please do answer that, and that will give us a sense of how we're shaping this webinar series going forward. So this time for real, without further ado, I am now going to pass over to Michael and ask him to present for us now today on greenhouse gas data. Thank you, Michael.
Okay, yeah, thanks, Ravi. Thanks very much for this introduction. Yeah, as has been said, my name is Michael Buchwitz. I'm from the University of Bremen. I was the leader of the Greenhouse Gas CCI project of ESA's Climate Change Initiative until end of last year, and now it's my colleague Maximilian Reuter who started with this beginning of this year. So I assume you all know that carbon dioxide and methane are important gases relevant for climate. So they are classified as essential climate variables, and the main role of the ESA CCI program is to generate ECV, essential climate variable data products. And in this presentation, it's about CO₂ and methane. So this is my slide to start with. I would like to show here the link between three different aspects. In the middle, you see satellite observations starting 2003. I will later tell you a little bit more about exactly what the data are that are shown here. But all the data I show you are satellite retrievals of column averaged dry air mole fractions. So these are essentially mean mixing ratios from the surface to the top of the atmosphere. So with the satellite data we are using, we cannot say exactly in which altitude, which number of molecules are, but we integrate it over the entire column. What you can already see here, that CO₂ here at the top and methane at the bottom, these atmospheric concentrations are increasing. And this is because there's an imbalance between the sources to the atmosphere and what is taken out of the atmosphere, so the sinks. You see here top left an overview about the global carbon cycle. We are presently putting every year about 36 gigatons CO2 into the atmosphere, basically from fossil fuel production and use, so natural gas, oil, coal. Not all this that we emit into the atmosphere remains there. The natural sinks, so vegetation over land and the ocean, basically take us the favor to remove half of the CO2 that we are emitting. But nevertheless, at the end of each year, there's more CO2 in the atmosphere than at the beginning of each year. Methane also has a number of anthropogenic and natural sources. Anthropogenic sources are also fossil fuel production and use, but also agriculture and waste and others. And a main natural source emissions from wetlands. Methane has a much smaller lifetime compared to CO2, roughly 10 years, and this is because of chemical reactions in the atmosphere. So basically, emitted methane is oxidized to CO2 by reactions with the OH radical. So in terms of causes and effects, we go from left here, from the source and sinks, to the atmospheric concentrations. And because these gases are greenhouse gases, and because atmospheric concentrations are increasing, this results in warming and other effects related to that, for example, increasing sea levels, melting glaciers, etc. And as you can see here at the bottom, CO2 and methane are the two most important greenhouse gases. So the cause and effect chain is going basically from left to right, from fluxes to concentrations to climate effects. But also show here with this light yellow, smaller arrow, that there is also a link from the middle here to the left. So we use basically the atmospheric observations, so the atmospheric concentration observations from satellites and other observing system to draw conclusions on the sources and sinks. And in fact, the main application of the satellite data is not so much to monitor the concentration in the atmosphere, but this can also be done very well with a sparse ground-based network, which provides much more accurate data, but also sparser data. But these global satellite data provide information on sources and sinks, and this is the main application of these satellite observations of CO2 and methane. Yeah, so we can use atmospheric observations of CO2 and methane to learn something about sources and sinks. There are several different methods to measure the concentration of these gases in the atmosphere. There are the in situ observations, which are very accurate, but not with global coverage. Satellites with remote sensing can give us a global picture, but with less accuracy. So, for example, these instruments listed here, SCIA-MACI, OCO2, etc., these are satellites that measure the vertical column of CO2 and methane since 2002, when SCIA-MACI on Envisat was launched. And there's also a network of ground-based measurements, TCON and COCON, so Total Carbon Column Observing Network, for example, that do the same thing, but from the ground. So they look into the sun and measure also vertical columns, and we use these data for validation, for direct comparison, because these ground-based measurements are actually the same quantity that we retrieve from space. So how do we measure what is our signal? The satellite is looking down basically and is measuring spectra of radiances, so light intensity as a function of wavelengths of reflected solar radiation. So whereas the greenhouse effect is related to absorption and emission of radiation in the thermal or infrared spectral range, the satellite data are measurements in the solar spectral range, so at much shorter wavelengths in the shortwave spectral infrared. And I show here examples how these spectra look like. Typically, we cover a relatively large spectral range from the visible to the shortwave infrared. And what you see here are radiant spectra, so light intensity as a function of wavelengths. Without, for example, these gases present in the atmosphere, you would have here straight lines. But because of absorption of these gases, for example, due to methane or CO2, you see these individual absorption lines here. So these absorption lines tell us, yeah, there was methane absorption or CO2 absorption along the light path. And the deeper the absorption lines are, the more CO2 or methane was along the light path. So what we basically do is the satellite measures these radiant spectra. We simulate the radiant spectra using wave transfer modeling until we get a good fit. And then this permits us to draw conclusions how much CO2 or methane was along the light path. So these radiant spectra are basically our input. They are called level 1 data products. And from these inputs, we generate a higher level data product called level 2, and these are the atmospheric concentrations. So basically using wave transfer modeling, we simulate the measurements and then can draw conclusions how much was in the atmosphere. What is shown here as an example for this atmospheric concentration map is a scene near Berlin where some power plants are located, and you see in wind direction, starting at the location of the power plant, elevated concentrations of, in this case, CO2. And with this observation and additional information like wind information, you can generate an even higher level data product, and this is emission or source sink information, the so-called level 4 product. So for this, you need, in addition to the observed mass increases, also the accumulation time, which is basically the length of the area of interest divided by wind speed. You may now wonder where the level 3 is. Level 3 is gridded level 2. So for example, monthly 1 by 1 degree maps. On this slide, I would put the greenhouse gas CCI project in some context, because there are other projects related to this. So the greenhouse gas CCI project from ESA's Climate Change Initiative started 2010, focuses on research and development for retrieval algorithm development to generate essential climate variables, so ECV, satellite-derived atmospheric concentration, CO2 and methane data products, meeting Global Climate Observing System, GCOS, and related requirements. And I will show you in a minute what that is. So we develop new algorithms or improve existing ones. And once they are mature enough, the algorithms and the data products, the plan is to use these algorithms for operational production. And we do this within 2 Copernicus projects. We generate long-term climate data records within the Copernicus Climate Change Service, C3S, and we provide near real-time data for the Copernicus Atmospheric Monitoring Service. And I'll show you on my next slide some results here. But there are also other applications in addition to research and development and operational. We also participate in other projects, for example, like this Medusa project, where we do detailed intercomparisons, what we do compared to what others do. So to ensure that what we do is state of the art and to learn something from these intercomparisons. We use our algorithms to provide or to generate methane emission information, for example, in the context of, for example, here this iClima EU project. And also we use our knowledge to give advice to ESA and others to improve future greenhouse gas satellite capabilities. So, and all these aspects are basically linked to greenhouse gas CCI. These 2 figures here, the time series and the maps, I've already shown at the beginning. The start here was 2003, this time series, thanks to the Skiamaki instrument on the ENVISAT satellite. But there's no single satellite that covers these more than 20 years time series. So fortunately, after ENVISAT stopped operation in 2012, we already had Japanese GOSAT data. Since 2014, we have NASA OCO2 data. And since 2018, we have GOSAT 2. And The time series that I show here and these maps, they are not only based on merging data from several instruments, but also typically there are several retrieval algorithms per sensor, and every year we collect all the state-of-the-art data that are not only generated in CCI, but also at other places in Europe or in the US or in Japan, and generate these merged climate data record data products. What is not yet included in the data shown here is, for example, the retrievals from the TROPOMI instrument on board the Sentinel-5 precursor instrument. I will show you some slides on methane from this instrument. And we are currently working on adding this to the next version of this Copernicus data set. And so the next release, when another year here will be added, would include also for the first time methane from TROPOMI. Okay. If you look at the CO2 time series, for example, it looks pretty boring. So despite climate agreements, etc., every year it's increasing and increasing. So it looks like a pretty straightforward time series. The only thing that varies is the seasonal cycle. So CO2 in the atmosphere gets up and down quite regularly every year. This is mainly because of uptake and release of CO2 by growing and decaying vegetation. But if you look at this data carefully and analyze it carefully, you will see that the growth rate from year to year changes a bit. For example, typically growth rate of CO2 is highest in years with strong El Nino, because then typically land sinks are reduced, so more of the emitted CO2 stays in the atmosphere. There may be changes from wildfire emissions, etc. It's similar for methane, where we had a kind of record growth rate around 21. This was reduced also to reduced sink, in this case reduced OH sink, reduced atmospheric chemistry sink. This was related to, for example, less NOx emission due to corona, and then due to atmospheric chemistry there was less OH, so also more of the methane emitted stays in the atmosphere, and there will also some other aspects like wetland emission, La Nina effects, etc. This slide shows an overview about past, present, and future greenhouse gas information providing satellites. So on the left, carbon dioxide, on the right, methane. So we do not have this armada of satellites here instantaneously. So this is past, present, and future. When I basically started working on this around the year 2000, there was empty space, nothing existed. Then in 2002, the first satellite was Envisat. And now we have many more satellites. Not all are dedicated greenhouse gas satellites. Some are, for example, like Prisma and EnMAP, they are primarily land missions, but they also cover spectral ranges so that it's possible to get, for example, methane information. So, and primarily because of the strong interest in methane, all people who were dealing with satellite data and who saw, okay, my satellite covers relevant spectral bands, can I get methane information out of it? And so this is an exciting growing area. Of course, in greenhouse gas CCI, we cannot deal with all these satellites. Initially, until recently, we focused on Skiamaki and Envisat, EASI, GOSAT-2 from Japan. At present, we focus on NASA's OCO2, Sentinel-5 precursor, Prisma, EnMAP, and EMET on ISS, and soon we will also add or start working with GOSAT-GW and Sentinel-5. Here I give you a little overview about what we actually, or more concretely, do in ESA Greenhouse Gas CCI project. Basically, every year we go over this cycle here of 5 tasks. The task 1 is the requirements analysis. Result of that is a user requirements document where the requirements are formulated. In task 2, algorithm development takes place. This is documented then in documents called algorithm theoretical basis documents. The improved algorithm will then be implemented, data will be processed, will be validated and will then be handed over to our users to see how useful these products are, for example, to get information on sources and things. So basically every year we go over the cycle and improve, extend the time series, improve the algorithms. Now, I start with task 1. These are the greenhouse gas ECV requirements. When we started around 2010 or shortly afterwards, we had this first GCOS requirements document, this GCOS 155. This was not specifically to our main quantities, so these column averaged CO₂ and methane, but there were requirements for tropospheric CO₂ and methane, which we interpreted as requirements relevant for us. And there was a very clear definition of what the greenhouse gas product should be. And this is written here, it's are retrievals of CO₂ and methane of sufficient quality to estimate regional sources and sinks. So the focus is here on regional. So regional means large areas, for example, the boreal forest in Canada or the Amazon or so. So at that point, the focus of the satellite observation, and it's still a key focus, is to learn not so much about emissions from individual power plants, but to learn something about the natural sinks, or the natural sources and sinks. So we want to know, is the Amazon a source or a sink? What is with the boreal forest? How is that changing with time? So the sinks was the initial focus, and therefore this definition of this ECV product. 10 years after, there was an update of this GCOS requirements document. There was then a clear move to smaller scales, including anthropogenic emission monitoring requirements. They mainly originate from requirements that have been formulated for the future European CO₂ monitoring, CO₂ emission. So these GCOS requirements, they cover a broad range of ECVs, so not only greenhouse gases, many others, and also not only satellite data, but also in situ, for example. We have a very dedicated user group who has formulated this user requirements document, and this is for CO₂ and methane from existing instruments, and covers requirements for regional scale fluxes and anthropogenic emissions. So this is more or less our direct user requirements document from our greenhouse gas CCI user group. And this user requirements document contains many details, but this is a kind of a key table which lists requirements in terms of random error, systematic error, stability, etc. There are other requirements, as I mentioned, from GCOS, but the numbers differ a bit from application and requirement source. But in summary, the summary is basically shown here. So requirements on the CO₂ retrieval, single observation, is very challenging. It's better than 1 ppm, which is 1/4%. Methane is a bit relaxed by a factor of 2, so 0.5% in relative terms, or better than 10 ppb. So these are basically our main requirements in terms of accuracy and precision. Now we go into the year 2000, when I made my PhD, and my PhD were basically 2 publications which appeared in JGR. The left one was on wave transfer modeling. So this is forward modeling. This is basically simulating the radiant spectra measured by the satellites. And the second was on the inversion, basically on the inverse modeling, or this is also called retrieval. This is given the satellite observations of the radiances, how to extract the atmospheric concentration information from that. And basically these 2 aspects, forward modeling and inverse modeling, is what we do since then, not only to get atmospheric concentration, but basically the similar approach of forward modeling and inverse modeling is also used essentially to get higher level product, namely these emission products. Also for that, you need forward modeling and inverse modeling. For the generating of the level 2, so the atmospheric concentration product, the forward model is the radiative transfer model. In order to get the emissions, the forward model is the model that takes the emissions and and simulates the atmospheric concentration. So we all have to do with forward and inverse modeling. And here I show you one equation. This is the so-called weighting function modified DOAS retrieval equation. On the left, you see here the measurements. This is the measured radiances. This is logarithm, but we don't care about this here. So this is the measured radiance spectra that depends on wavelengths, but also on the vertical columns, for example, of CO2 we are interested in, other parameters. And on the right, you see a model of that. This is a linearized radiative transfer model. So we select a linearization point. So for example, we roughly know how much CO2 is in the atmosphere, but then we also have the derivatives here and these times fit parameters. And so the question is, what is the mean radiance and how does it change if we add, for example, CO2? And then we also have another set of parameters here. These are parameters of a low order polynomial because, for example, surface reflectivity may change smoothly with wavelengths, but our main signal is this differential signal from the absorption line. So we separate basically the absorption signal from broadband features, and this is what the polynomial is doing here. So you can cast this into vector and matrix notation, formulate this as a least squares problem, solve with respect to x. This is the state vector that can contain, for example, the vertical column of CO2, methane, etc. So when I did this in 2000, Envisat was not launched. The launch was 2002, so this was all based on simulations. Now we are 25 years later. This WF-DOAS algorithm still exists. My colleague Oliver Schneising applied it extensively over the past years to TROPOMI to generate a very high quality methane data product. And I will show you later some results. You can also see here already maps and validation results. And so where this equation here is still at the core, there are still a large number of other things that need to be done in order to generate a high quality data product. And this is, for example, quality filtering, bias correction, making it fast enough, so designing an appropriate lookup table, etc. So on the left, this is the WF-DOAS method I just explained. This is this least squares method. This is applied to relatively small spectral range, around 2.3 micrometer. Methane is absorbing in the spectral range. Water is nearly everywhere. CO, so CO, carbon monoxide, is retrieved also here in the spectral region as a second product. Most people use more complicated algorithms, for example, also to solve a more complex problem. For example, as I already said, that CO2 requires higher data accuracy, and this can be done with a complex algorithm. So there are additional terms here in this equation. For example, this XA and this SA, and this A is here for a priori. So this optimal estimation or Bayesian inference, you use a priori information to constrain the retrieval. You then try to not only retrieve the vertical column of CO2 or methane in one shot, as we do for these WF-DOAS, but you try to retrieve a vertical profile, and this means to constrain the retrieval. All retrievals typically consist of three main processing steps. The first is pre-processing. This means read the satellite data, but also read additional data, for example, meteorological data, the temperature profiles, pressure profiles, etc. And you may also do here some checks if there's too much cloud so that you do not look down to the ground, and then you can already stop here maybe in pre-processing. If all assumptions are valid, so for example, not too many clouds, then processing goes on with main processing. This is then, for example, solving this optimal estimation equation here. And the final step is then post-processing. And this means a bias correction and quality flagging. So for each single observation, we want to know if the retrieval was successful or not. And this is where we use heavily machine learning to do this post-processing. So I showed you our task one, these are the requirements. This user assessment is the last step. And in the remaining of the talk, I will show you what happens in between. But once we have generated a new data products, in our last greenhouse gas CCI task, we hand these data products to our users who make an assessment of the atmospheric concentration ex CO₂ and ex methane products to see what their information content is with respect to surface fluxes. You see here examples for CO₂ or for methane. And because this is a very challenging application, and even small errors in the satellite data can result in significant errors in the fluxes, the users typically do not use only one satellite data set as input, but several, and they do then comparison and see in order to find out which signals are stable, which signals depend maybe critically on a certain algorithm. So I've got time to say much more about this at this stage here. So if you're interested, go to the Greenhouse Gas CCI website. So all documents are there, including this climate assessment report document. Now, I would like to focus on methane. I think you probably have all heard about this global methane pledge. This is an initiative from, I think this is now more than 150 countries who this has been established in 21 at COP26, and participants joining the pledge agree to take voluntary actions to contribute to a collective effort to reduce global methane emissions by at least 30% from 2020 to 2030. So this is a challenging task, 30% reduction in just 10 years as a global and not as a national reduction target. So it's a global goal. So there's high interest now, not only in CO₂, but also in methane. And this methane pledge agreement is showing that. The methane pledge requires appropriate input data. And for example, UNEP has launched the International Methane Emission Observatory, IMEO, to collect data on methane emissions. And they part of that is, for example, this methane alert and response system MARS, where they collect and made available estimates of methane emission from satellites. And also Europe has a system providing a methane hotspot information called CAMS Methane Hotspot Explorer. And here data from Sentinel-5 precursor are analyzed with respect to the information content on localized emission sources. So there's a lot of interest in methane, and there are already first services to provide relevant information in the context of the global methane pledge. I showed you already that there are already many satellites available in the past, now, and planned for the future, but they all have very different characteristics. For example, Skiamakio and Envisat provided global coverage, but spatial resolution was pretty poor, 50 kilometer. So this was then improved to 10 kilometer with GOSAT, but there is no global coverage, but the individual satellite observations have 200-something kilometer distance between them. On the other extreme, there are the high spatial resolution hyperspectral imagers, such as ENMAP or EMET. They measure at a resolution of 30 meter or 60 meter. So with this, you can nicely see emission plumes and can really pinpoint to the location, to the borehole or whatever is emitting. So you can then detect major emission sources, quantify the emissions. But they can only look at specific targets. So with 30 meter globally, we do not have global coverage, but they look at specific targets. For example, at targets that have been identified by analyzing TROPOMI data. TROPOMI has global coverage, so you can get the global picture. The spatial resolution is 6 kilometer, which is, of course, much worse than the 30 meter. But here you have the global view, and you can identify major local emission sources, and then you can use the other instrument to get more detailed information. So basically, the combination of this global lower resolution view from TROPOMI plus the higher resolution data from other satellites. So this combination is used to currently get high quality information on methane sources. When we had the first, in this case, 2 years of our TROPOMI methane retrievals, we used a cross-sectional flux method to obtain methane emission information for various large oil and gas fields. We quantified not only the emission in terms of here megatons per year, but also estimated leakage rates. And this is important because there are ongoing discussions to what extent burning natural gas, which is mainly methane, is better for climate than burning coal in terms of energy production, because typically less CO₂ is emitted if you burn methane compared to burning coal per amount of energy. But this is only valid if methane is not leaking directly from the oil and gas fields or during transport into the atmosphere. So, and typically, leakage rate should be very small, ideally less than 3% or so, to have this methane benefit over burning coal. We used this TROPOMI methane data set here when we had the first 4 years with this version 1.8 of this WF methane retrievals, and looked at where we see basically permanently elevated methane, at which locations. We identified 217 so-called potential persistent source regions. The top 10 emission areas are discussed in this publication here of my colleague Steffen Vanselow et al. So if you would like to see more about that, please have a look. Although this was all done with this version 1.8 of the algorithm, and typically we thought, okay, this is maybe our latest version, but then we analyzed it carefully and found some problems. For example, we saw a region of elevated retrieved methane over the Baudelaire Depression in Chad. We analyzed this and identified that this is not a local methane source, but a retrieval bias due to challenging retrieval conditions. You have here a very bright surface combined with a heavy desert dust storm, and this relates in this artifact here. And my colleague Oliver Schneising then tried to improve this algorithm using machine learning, basically, to improve the quality flagging, but also so that these artifacts are not part of the product anymore, but also at the same time to increase the yield, so the data coverage where possible, for example, here at high northern latitudes. So this latest version, very new, is now this version 2.0 product, which has better accuracy and precision, and for many regions, higher data yield. This version 2.0 product has been validated. For this, we use the TCON network, Total Carbon Column Observing Network. You can see here where the TCON sites are. This shows here detailed results, but in summary, the precision is roughly 0.5% or 13 ppb, and systematic errors are smaller, around 5 ppb. So this product has very high quality. These data products are used by several groups to look at different aspects. For example, what is with methane in India or northern high latitudes or Europe, and including comparisons with other products. So for example, the operational product or the product generated by Esron. So there are several publications, and they are listed on the Greenhouse Gas CCI website where the data products have been used. Now for the final 5 minutes, I think I would move to these hyperspectral imagers. I already showed you this a figure here with the 30-meter Nmap retrievals, which permits us to really get very detailed emission plume information, including identification of the location of the emission source. There are several algorithms to obtain emission information from these emission plumes. So a nice summary is in this NIST document here, common practices for quantifying methane emissions from plumes detected by remote sensing. This figure is from that publication. There are several methods to use. Our preferred method is the cross-sectional flux method. I already showed you some examples of that. This method is basically based on integrating column enhancements across the plume or across a wind direction times wind speed, and this gives you an estimate of the emission. There are other methods, and in several projects we compare results from different algorithms. But we use this cross-sectional flux algorithm. But this is a level 2 to level 4, so from concentrations to emissions. The first step is the level 1 to 2 processing. This is getting the methane enhancement maps. And focus of greenhouse gas CCI is level 2 products, not so much the emissions, although we also do that, but the main focus of greenhouse gas CCI is take the radiances and retrieve atmospheric concentration information from them. For this hyperspectral imager, we use a weighted linearly squared method, and currently we look at different approaches. For example, this physics F method uses a low-order polynomial to consider variations of surface reflectivity, so this is very close to DOAS. The principal component analysis method is not using polynomials, but principal components. And currently our baseline, and this is also the method most other people working with this data use, this is called matched filter. There's no use of a polynomial, but the basic idea here is to use the measurement error covariance matrix that you also need for this linearly squared method directly from the image. And this is, we are still looking at all three methods, but focus also in terms of emission results, we use currently as baseline this matched filter method. And this has been used then in combination with the cross-sectional flux method to get the emissions, for example, to obtain an overview about European methane emission sources. This is documented here in this iClima report, inventory of point source emissions of methane estimated from high-resolution satellite data. This document is available from the iClima website. This contains tables like this, for example, for estimates of landfill emissions and our results compared to what others do or get from other satellites, for example, for Carbon Mapper, whereas we use, for example, Nmap or EMIT. So if you are interested in that, please have a look at this document. In order to validate the emissions, we also participated or still participating in a Stanford, Michigan controlled release experiment, which started in 2024, but the focus was 25. So this is a single blind test. So we only know where the emissions are released. We do not know how much. And for example, this is our results from the first phase in 25, January to March. We downloaded the satellite data, applied our level 1 to 2 and 2 to 4 emission estimates to that, obtained emission estimates. In green are the ones which have quality flag goods. Red are where we think we cannot do a very reliable emission estimate. And we supplied this data then to the Stanford team in April, and after all teams participating in this exercise have submitted their emission estimates to Stanford, they unblinded the data, so they gave us information on the true information, on the true emission, so that I can make a plot like this. And when sawing that, I was really quite happy because these emissions are very small. So this is really near the detection limit. So they cannot release really huge amounts of methane, but this is all around the detection limit. But you can see that even for that we get quite good results. Most of what I showed was results that we produced in Bremen. I want to show here that there are many other groups who work in this area in Europe, but also in the US and elsewhere. I want to just show you here that there are many other groups who publish very interesting publications on this growing topic. Nearly my last slide. So I've had to focus on methane because of time. We started already more than 10 years ago to improve CO₂ measurements from space. We initially proposed the CarbonSat mission to ESA for Earth Explorer 8. It was not selected. We were 2 from 40 or so, I think. But basically, the CarbonSat specification has been refined over the last years for the CO₂ mission, which will be a series of 3 satellites from the European Union in the context of the Copernicus project. So it's built by ESA. A data processing level up to level 2 will be done at EUMETSAT. Higher level data processing emissions will be done by Copernicus Atmospheric Monitoring Service. And CO₂ will be 3 satellites. The first one probably launched in 2 years, and characteristics, source, ground pixel size, etc., will be similar as we have proposed for CarbonSat. And although the name is CO₂ monitoring mission, it will also provide very good methane. And these are the key takeaways. So CO₂ and methane are essential climate variables. Focus of greenhouse gas CCI is to develop and improve retrieval algorithms to generate satellite-derived CO₂ and ECV data products, meeting GCOS requirements. Relevant quantities are the column average mixing ratio, X-CO₂ and X-methane. These products can be retrieved since 2002 thanks to SCIAMAC and ENVISAT and similar follow-on instruments or satellites like GOSAT, OCO2, Sentinel-5 precursor, and more recently also thanks to high spatial resolution imagers like PRISMA, ENMAP, EMAP, GHG-SAT. So the corresponding data products are used to obtain information on sources and sinks of these important greenhouse gases. Currently, there is huge interest in methane, as reducing methane emissions can slow global warming, so therefore the Global Methane Pledge initiative. Space-based observation of CO₂ will be improved thanks to imagers such as GOSAT-GW and CO₂M soon and in the future. And last but not least, I would like to highlight that greenhouse gas observations from space is an important and growing research area, and a lot has been achieved in recent decades, as I hope I've shown you, but much more still needs to be done, as our knowledge on the various natural and anthropogenic sources and sinks has still large gaps. And this is really my last slide. So I had to think about a lot, what can I say in this roughly 40 minutes and what can I not say? So a lot of things I could not say. If you're interested in our data or documents or publications, please have a look at the Greenhouse Gas CCI website. As I said, I've already said, science leader now is Maximilian Reuter. I was science leader until end of last year. Now this project is in the very good hands of my colleague Maximilian Reuter. These are contributing institutions. And with this, thank you very much for your attention.
Excellent. Thank you so much, Michael, for such a comprehensive overview of this field. Really appreciate it. And we have had some interesting questions coming through, so we're going to turn to those in a moment. Just to remind everybody that you can still submit questions either via the chat or the Q&A box, and we're just going to go through a few of those in just a moment. But I'm going to begin, Michael, with a quick question from me, if that's okay, which is, What you've reminded of us of in this talk today, apart from the very specific insights and the technical methodologies that are used and so on, is also just the sheer depth and detail that exists in climate science, and the number of parallel activities that are taking place amongst groups all over the world to really scrutinize the data and to develop products that provide insights that hopefully eventually can turn into actionable information for policymakers and so on. What's your feeling about the general status of that bridging from science into policy and decision making at the moment? Do you feel there's enough awareness of how much detail goes into the science and how much scrutiny that you give each other within the field before presenting results and information for decision makers and policymakers?
Yes, so I think the satellite data, especially in terms of the derived emissions, is already used quite a lot. So these data are feeding the UNEP services on methane, for example, for these IMEO and MAS systems. So this is already high on the agenda on United Nations Environmental Program. And also in Europe within the Copernicus system, so also the European Commission are aware of that. So I already already years ago I saw presentations from the Environmental Protection Agency in the US, which now is not anymore in the situation they were a few years ago, but okay, that's another story. They clearly showed how they use that. So they see the emission plumes and where it's originating from. So this is actionable information for them because they see, okay, it's power plant X or a landfill Y. So they know where emissions happen. They can contract the industrial consortium or the owner of the landfill or whatever, and can get in contact with them. And then later, once they have fixed that leak, you can look again and then see, this feedback from space helped to fix that leak. So this is the most direct. Yeah, so I think it happens.
It's happening, yeah, and I think as the technology develops, as the number of sensors increase, and indeed as the visualization techniques improve, I think you're right that very direct, seeing what's happening, seeing the implications, connects with more decision makers and policy makers. You're also a very experienced communicator and educator. You've taken part in some of the courses we've produced together as well in the past, and I guess you'd say that that's a crucial part of this, to continue that momentum of engagement and communication and education in the broadest sense of those with the decision-making power. Would you say?
Yes, and even there are already companies who try to do that commercially. So this means there are people who pay for that, for this information. So, and we have also been asked in the past by big energy companies, could we do this and this? For example, monitoring that they extinguish fires somewhere in China, which emit a lot of CO2 because there's burning whatever. And so there are many there are many applications. So where I had to say in the past, no, sorry, this is beyond our detection limit. So if detection limits get better and better, there will be more and more applications. So what is relatively easy is if there is a very localized source with an intense emission, but already a city where everything is more spread over a larger area is already much more difficult. So although I showed this armada of satellites, so the knowledge we really would like to get, also in terms of climate agreement, is much more ideally hourly for different sectors, etc., etc., etc. And in fact, we can only do a part of that, but it's improved. Yeah. it's improving.
Things are moving. Okay, well, thank you. In the meantime, while we've been talking, we've had a surge of questions coming through, so I'm going to turn my attention to those now. And we are going to probably overspill the hour, and I hope some of you can stay on with us, but we may run out of time to cover all questions. So, Michael, if you're willing, I wonder whether we might be able to circulate some additional responses to some of these questions after the webinar, if we don't get through all of these today. So, just starting with the first one here, there's a question. Recent developments in the US have resulted in the decommissioning of the CO₂ mission. What would be the effect on the modelling when this data source is no longer available? And does ESA have enough capacity to fill the gap? And I think you spoke to that a little bit with the forthcoming missions, but maybe just your take on the status of that particular mission and the implications.
Yeah, so CO₂ is a key mission. Very precise retrievals of CO₂ is possible with that. So it's a quite large team working on that. So there's no, so if this mission is, I don't know, failed because it's already pretty old or switched off for whatever reasons, there will be a big gap. But fortunately, the Japanese, they have a really long-term plan. So they had GOSAT, then GOSAT 2, they now have GOSAT GW, which, so not all is lost, but every mission is important. Yeah.
Absolutely. The next one here, I think you sort of touched on a little, but I'll read the question anyway. The question is, do you also provide long-term regional trends, e.g. over the past 2 decades of CO₂ and methane fluxes? What are your thoughts there?
Yeah, so well, what we look at are the annual growth rates globally. We also look at kind of latitudinal bands, but mainly in order to get regional information. This is not done what we do in Bremen. We give data products to others. So there are these modelers. They have global models. They take the observed atmospheric concentrations and basically fit that in their model. They can change the surface fluxes regionally, for example, 1 by 1 degree, monthly fluxes or whatever, or different categories, rise and for methane also. So they use these. They basically go the step from the atmospheric concentration to the spatially and temporally resolved fluxes, and then they see they compare with our current knowledge, for example, and they can see, oh, over the tropics there are larger emissions of CO₂ compared to our knowledge, etc. And then one has to find out, what exactly the new knowledge is that the satellite brings, taking into account all the uncertainties, because there's uncertainty in our pre-known knowledge, there's uncertainty on the satellite data. So typically they do that a little bit like detectives, not only having one data set and noodle that through their system. They use different input data to see what is stable, what is not. And in particular for methane, a lot has happened. CO₂ is a bit more difficult.
Thank you, Michael. Just moving on to the next one here, slightly off the technical topic into sort of some broader thinking here. On a yearly basis, individuals and organisations at the COP meetings, the UN COP meetings, make pledges to reduce greenhouse gas emissions. Yet you've mentioned something relating to emissions increasing at the end of the year past the values recorded at the beginning. How can we distinguish between genuine commitments and pledges that serve more as financial or reputational tools? That's the question.
Oh. Yeah, so maybe the most advanced step in this direction is the question: to what extent can satellite data already now contribute to, for example, these global stocktakes? I mean, financially, and to really. So there are publications on that showing per country and then comparison with what the countries reported, etc. And where does that agree and not agree? With respect to financial applications and legal aspects, maybe this is the next level. Then I would say you have to be 100% sure, and could be difficult.
I think there's a whole seminar just on that question alone. So moving on to the next one, where we have a question here regarding, well, it's I'll read it to you. Are there some level 5 products designed for policymakers? Is the first part of the question. It relates to some of what we touched on already, I think. Is accuracy lower in Africa because of the lack of TCCON instrument? And then the final part of this question is, why has space-based EO not been included in governance processes, i.e. the global stock take of the Paris Agreement? Well, I mean, I think you've just referred to that, and of course it has, but I'll let you respond on those 3 points.
Okay, I forgot the first question.
Okay, so are there specific level 5 products designed for policymakers?
Well, the question is what they need. I assume they are not interested in atmospheric concentrations, they're interested in emissions. And in that sense, yes, but they may even need higher level data products, even higher level in terms of, I mean, so yeah, I think this may go back to the global stock take. So the countries have to report their emissions basically every 5 years in this global stock take process, and most of these emission estimates are coming from so-called bottom-up methods. This has nothing to do with satellite, or this can, but typically this means multiplying 2 numbers. One is activity, the other is emission factor. So activity could be tons of coal burned, and emission factor is how much CO2 is emitted per kilogram coal or so, or number of cows times methane emission per cow. So you can do very detailed, if you know the number of cows, you know something about the methane emission. If you know the number of coal burned, you also know something about methane emission. And you can make this very detailed based on economic data. We satellite go the other way from top down. So we observe literally from space, from the top. We look down and see what's in the atmosphere. So we see the accumulated emissions, so the impacts, so the net flux to the atmosphere. Sometimes we can say, as I've shown you in these emission plumes, oh, this is coming from that location. This is methane coming from exactly that location. Emission is that strong. But it is another story to get an annual emission of a country. And maybe even per sector, like what is traffic doing and what is heating doing. So what the goal is to bring this together, so to basically to check with this top-down view, is the bottom-up reasonable, or are there large discrepancies? For methane, we often see large discrepancies, so the reporting and this is not always fitting. So in a sense, with this satellite data, we can kind of check, or we can also say control, if this bottom-up makes sense, or if it's reasonable, or it would be even better if we can help the reporting. We can help the country report. And there are countries who use the satellite data also for their reporting. So in that sense, it's highly policy relevant, I would say.
Indeed, and it's worth just perhaps saying as well briefly that, of course, there is a thriving European Earth observation sector with many companies who are innovating in various ways of creating new and very specific data products that leverage all sorts of techniques and data fusion methodologies, and of course AI and so on as well. So as things evolve, there are more and more specific tools available to policymakers that are derived from the data. Yeah. There was one other additional point in that question, which was around the detail available in across the African continent, I think. Did you want to comment on that briefly?
Well, with the African continent, it's in the north, it's mainly the Sahara, so there are not so many sources. Then there is the tropical belt where there are lots of clouds, which is also not so good for us. So we have large data gaps where the clouds are. We have to look down to the we want to measure radiances, that is solar radiation reflected at the Earth's surface, so that the solar photons basically go from the sun to the Earth's atmosphere, hit the ground, and then are scattered or reflected towards the satellite, and then detected by the satellite. So if there's a cloud, we cannot see what happens at the ground. So, and because of the very demanding requirements we have of fraction of a percent, we have to identify even the slightest amount of clouds. So cloud detection and flagging data bad that are cloudy is a big step of our retrieval algorithm. So, and the other thing with Africa is that there are hardly any data to compare with, so that we are often not so sure how accurate our measurements are there. My boss, Professor Bösch, has now connections to parts of Africa where he's establishing measurements. But so far, the TCON, for example, there are no TCON sites. While we are not so sure, I would say we are not so sure about the African data because we have nothing to compare, and there may be good, there may be specific issues, but yeah.
Thank you, Michael. Yeah, and indeed, just as a little bit of extra wider context, of course, the African space sector is fast growing. There is, of course, now the overarching African Space Agency, which is acting as a sort of integrating umbrella across various national space agencies and many emerging startups. So I'm sure we'll see that picture starting to change. But thank you for that. We are going to go on for a few more minutes, if that's okay with you, Michael, to try and cover a few more questions. I think we'll try and end by 1/4 the hour, if that's okay for everybody. So moving on to the next one, we have a question here, which I will read out to you. Thank you very much for the insightful and clear talk, Michael. I was wondering about the temporal consistency of the 20+ years data record, which harmonize or fuse data from different sensors and algorithms. For causal attribution inference research, my colleagues are typically conducting. Often the identification strategy relies on year-to-year variations at the grid cell level. So detailed questions, so bear with me. An experience we have with other long-term harmonized data sets on land cover, such as ESA GHG-CCI land cover, and some others, is that some year-to-year variations might be more likely with abrupt change due to data or algorithm fusion artifacts rather than real. Though that remains to be validated, cross-triangulated. I'm wondering if the CO₂ and methane annual estimates here are expected to be mostly free from such possible artifacts, or if it is not recommended to interpret the data at that spatial and temporal granularity. Thank you. Here you go.
Okay. Yeah, so we put a lot of effort in generating these harmonized long-term data set. This started in greenhouse gas CCI many years ago because I thought it's simply nice for many users who are not the super experts, maybe, who they don't worry, is it this satellite, that algorithm, this satellite, that algorithm. They said, could you not give me the longest possible time series, harmonized, and I would like to look at what is over my country or my research area, etc. So others said, this is totally useless. Don't do this harmonization. Focus on the individual products, make them as good as possible. But we said, why not doing that in addition? So, and we thought about how could they be merged in a kind of optimal way. And when we did that, this was mainly my colleague Maximilian Reuter who developed this algorithm. He proposed an ensemble approach for this merging. So what we did for several years is every year we contact all the people in the world who generate high quality data products. This is not only greenhouse gas CCI. We contact NASA for the latest and greatest CO₂ product, and the Japanese team, and every group in the world. And then the question then, so we had several satellites and several data products per satellite. And the idea was then, the core idea of this algorithm was to compute per grid cell, so to say, the median of the data product. So our assumption was that, so we harmonized the data product in many different ways, also with respect to differences what could come just from different assumptions in the retrieval algorithm. For example, I mentioned this a priori information that has been used. So we try to bring them all to the same level, and then to use the median. Our assumption is basically the median is better than the individual products. And in fact, this turned out when we validate the data with the TCON network. So we think we did a very good job, so that residual errors are small, but definitely nothing is 100% error-free.
Okay, thank you. A very helpful answer to a very detailed question. Super. Quite the opposite end of the spectrum. Now we have a very simple and specific question, which is, which satellite captures emissions data from wetlands?
Basically, every satellite that measures methane. The question is only, how accurate is this? There are these dedicated the greenhouse gas satellite like GOSAT-2, a Sentinel-5 precursor in these methane band. We even had this with the first instruments, Skiamakio and Envisat. This has nice methane observations. So there are other satellites, especially those who are not dedicated to do methane. They also provide methane information, but they're noisier. But there are many satellites providing methane information from wetlands.
Thank you, Michael. We've got a few more to go, just very briefly, if we could quickly rattle through these. There's a question here regarding how do you attribute the methane to oil leaks? What's the confidence range?
This is relatively easy. If we use a satellite where we can really pinpoint to the location of the emission source. So typically this requires this 30-meter, 60-meter hyperspectral imager like Nmap and EMIT, etc. But if it's strong enough, we can also see this with TROPOMI because they have 6-kilometer resolution, so this must be really a massive. Although I showed you this example for the large oil and gas fields. So, for example, when we first analyzed the TROPOMI data with this relatively low spatial resolution but good coverage, my colleague basically obtained emission estimates from entire oil and gas fields, like the Permian in the US, and so really big oil and gas fields. For example, for the Permian, our first emission estimate was around 3 megaton, with a significant uncertainty of, I think, a megaton or so 3 plus minus 1 or something. And in parallel, there was another group using another approach, also other input data. And they also did what we did, namely not only providing emission estimates, but also computing leakage rates. And we were not aware that what they were doing, they were not aware what we are doing, but our paper shortly appeared after their paper. And we both came up with these roughly 3 megatons, so very similar number. And their paper was very high in the media because they reported a quite high leakage rate. So this was a bit alarming, whereas ours is a bit moderate because, well, for certain reasons. And so this was kind of one of our first attempt to get methane information from oil and gas fields. That was very, very good because we had this independent check with what others did, totally independent. But yeah, we continue more and more with this, and sometimes agreement is very good, sometimes emission estimates differ. So it's still a kind of an ongoing research effort to find out what is the best method, how how good are our uncertainty estimates, etc. And this is what ongoing in different projects currently.
Great, thank you, Michael. Just the last couple of questions here then. One of them relates, I think, the answer I'm sure will be very similar to what you've just outlined. The question here is it possible to also use satellite estimates to quantify how conflicts contribute to methane emissions?
Oh, with conflicts, you mean war? Or...
I assume, yes.
Yeah, okay. Well, in principle, yes. That depends on what is actually happening. So it must have a big impact on the emissions. So, for example, if there's a large oil and gas field and during this conflict, production will slow down or the other way around, and the emission is large enough, we can detect that and quantify that. But I'm currently not available of a specific publication where this specific aspect has been discussed in detail. But in principle, yeah, if the emission change is large enough, then yeah, can be seen.
Thank you. And last but not least, we have a question here actually from Simon Pinnock, a colleague at ESA. Thank you for joining us, Simon. Good to have you with us. And Simon asks, what are the key challenges to integrating the information from the different satellites that observe at different scales?
Yeah, so we and others, or mainly others, tried to compare data from this TROPOMI instrument, which has a 6-kilometer resolution, compared to the high spatial resolution, 30-meter, 60-meter satellites. And this is quite challenging because there's a large difference between 30 meters and 6 kilometers. And so in this big 6-kilometer footprints, you may have lots and lots of individual sources. Some of them you may not capture with the with the high spatial resolution because they do not cover this large area, or the detection limit is below their detection limit. So this is an ongoing research effort to compare the results at the different scales. People are working on that. There are publications on that, but it's an ongoing activity, I would say.
Indeed. Well, thank you very much, Michael. Thank you for fielding all of these quite diverse questions, and thank you all so much for submitting those for us today. Well, I'd like to sort of bring things to a close at this point, and to thank you once again, Michael, for a really fantastic overview and responding in such detail on each of these points. Really great to have you with us, and congratulations on your incredible work over the last decades, indeed. And it's, of course, an important moment for you as you move on and hand over the leadership of the CCI project on greenhouse gases. And thank you for all the incredible work you've done. Before we go, I just want to quickly plug, well, the rest of the series. As we mentioned, this is a new webinar series we've added to the CCI Knowledge Exchange activities, focusing on a range of climate topics. And indeed, we're actually joined in the audience today by leading climate scientist Annie Kaznav, who's actually going to be hosting the next webinar for us. So thank you for being here with us today, Annie, and for asking a question earlier as well. The next webinar, which will be presented by Annie, we'll be focusing on altimetry and sea level rise, and how it's an indicator of climate change and how changes in the trends can signal broader climate shift. So we very much look forward to that, and very much hope that you'll all be able to join us next time for that one, and indeed the further webinars that we'll have in this series going forward. So please do look out for further announcement of the rest of the series, and indeed do visit the climate website on the ESA site. The details are there for you on screen, and do engage with some of the other tools and data information that's available on the overall site. So thanks again, and we hope to see you next time. Have a good day.